This is lecture 7D for Calculus 2 on the use of partial fraction decomposition to evaluate the integrals of rational functions. The reason that rational functions can be integrated by the method of partial fraction decomposition is that the integrals that result from partial fraction decomposition are very easy to evaluate. And I've given a list of the main ones right here. I'm using k as a constant of integration instead of c, because in a partial fraction decomposition you end up with usually uppercase A, B, C, D, or whatever, however many fractions you end up decomposing into. So I didn't want confusion between the c of the partial fraction decomposition and the constant of integration, so I'm using k here. But I have made a list here of the common ones that you will use when using partial fraction decomposition. The first is just the integral of 1 over x, which is natural log of x. And that's this line right here. Okay, 1 over x minus a raised to the nth power, and here n will be greater than 1. That can be evaluated using the power rule. When the fraction cannot be, the rational function cannot be decomposed completely because of terms like x squared plus a constant number, you can't decompose that into rational functions. Into real numbers, you'll end up with complex numbers. So you leave it as, for example, x squared plus a. Then you end up with this other terms, x over x squared plus a, in your partial fraction decomposition. This is also easy to integrate. It is the natural log of x squared plus a. You can evaluate this integral using substitution. Just let u be x squared plus a, and then du is 2x dx, and then you can work out the integral. Okay. I'll get rid of some of that on here. So that's another one that's used commonly, and the other is 1 over x squared plus a, which is the primitive of 1 over x squared plus a is the arctangent function. So if you keep a list of these handy, these four right here, you can use this partial decomposition easily. So I'm going to write the rational function as p of x over q of x, where p and x are polynomials. I'm going to assume that the degree of p is less than the degree of q. If it's not, you need to divide the rational function first, just using polynomial division. And there are two main cases. I'm going to say most about the first case. The second case I'm not going to say a whole lot about. Here's the case we hope either we have or we can achieve. But you have a rational function. For simplicity, I'll write it as an example, 1 over x minus 2 squared times x plus 3. Now the denominator can be factored completely. You can decompose this into partial fractions. Here's the ABCs, which are the coefficients of the partial fraction decomposition. First term would be x minus 2 squared, because you've got the square in the original denominator, and then the last term is c over x plus 3. Now when you integrate this rational function here, you break it up into the partial fraction decomposition, and using the linearity of the integral operator, you can integrate each one of these separately. A over x minus 2 becomes a times the natural log of the absolute value of x minus 2. B over x minus 2 squared by the power rule is minus b times x minus 2 to the negative 1. And then for the third term, it's c over x plus 3. This integral is c times the natural log of x plus 3, and then, of course, you only need one constant of integration. And that was very easy to do. Here's an example, another example. Trying to integrate 1 over x squared minus x minus 20. You can factor the denominator into x minus 5 times x minus 4. Partial fraction decomposition gives you a over x minus 5 plus b over x minus 4. Both of these integrate to natural logs. Finding A and B is just an algebra problem. I'm not going to say too much about this here. Both calculus books go into different methods to evaluate those coefficients A, B, C for your partial fraction decomposition. The easiest way to do it is to multiply both sides by the denominator, so you end up with something. In the last example, for example, you end up something with like this: 1 equals A times x plus 4 plus B times x minus 5. Then you do something that doesn't seem exactly right. You set x equal to minus 4 or x equal to 5. Of course, those are not in the domain of the original rational function, so it doesn't seem quite right to use them, but that's one trick to find values for A and B, and there are others. In the case 2, you end up with these irreducible quadratic forms in the denominator. Here are two of them, x squared plus 2 and x squared plus 3. Those cannot be reduced, at least since we're dealing only here with real numbers. You end up with forms that look like this. I'm not going to say much more about it. Every instructor has things they are more interested in, or other topics in the semester they consider rather trivial, or that's what I think of partial fractions. At any rate, they're pretty easy to use. The idea is you have a rational function, you make the partial fraction decomposition, and you go back to, let me go back to the original slide here. Okay, you end up with terms that look like this. All of these terms are easy to evaluate. 1 over x minus a is a natural log. 1 over x minus a raised to the nth power, where n is not equal to 1. You can use the power rule to evaluate that. X over x squared plus 2, if you have an irreducible form, again another natural log. And 1 over x squared plus a is 1 over a times the arctangent. And that's basically all there is to it. I will not give you any long homework problems or exam problems where you have to find those coefficients A, B, C for the partial fraction decomposition. I think that's a topic for algebra.